Hi everyone, this is Kathleen Quach, and this week I'll be talking to you about probability theory. Today's lecture is about counting and set theory. If you have any questions, please feel free to email me, and with that, let's get started. So there are three reasons why I think probability theory is confusing. The first is you don't count properly, and counting is super important for figuring out the size of your sample, which has important consequences on what your probability values actually are. Secondly is you don't know definitions, and definitions of things like probabilities, what kinds of probabilities, and the different operations. And then finally, your intuitions are wrong, by which I mean you don't understand or you don't have a good sense for what values probabilities are likely to have. And hopefully by the end of my two lectures, we'll have addressed these three issues. Okay, so let's talk about this lecture, which is about how to think about like groups of discrete elements. And we're going to start with the concept of counting. So to sort of illustrate what I mean by counting, I'm going to give you an example. So you have a problem, and there are 25 million licensed drivers in California. And assuming an average of one registered car per driver, how would you design a license plate code to create unique identifiers without compromising legibility? And we want to do this in a way that is smart and not hard, trying to enumerate each individual combination would be terrible and tortuous. So let's figure out a smarter way of counting, and every concept of counting is going to be based on this, which is the fundamental theorem of counting, which says that if a job has k separate tasks, and the tasks are enumerated by I equals 1 through all the way to k, then each I task can be done n1 ways, then the entire job can be done n1 times n2 times all the way to nk ways. Now it's super important to realize that these different n values don't have to depend on each other. They can be completely different from each other, and they only have to refer to their individual task. So these different tasks could be all kinds of crazy things and unrelated to each other, and they'll have their own number of ways of being done. So let's give an example. Let's go back to the California license plate example. So the way that the base plate code is developed is the first position is always a numeric. The next three characters are alpha, and the last three are numeric. And just remember that there are 10 numeric possibilities, and then there are 26 numeric possibilities from the letters of the alphabet. Okay? It gets a little complicated. There are rules about the alpha positions next to numeric positions, and that particular rule is that those alpha positions number 2 and 4 cannot be I, O, or Q, and that's so that they're not confused as numbers. Okay, so let's figure out the numerical calculation of this. So position 1 only has 10 to choose from, 10 numeric, so that's 10 times 23. 23 is because you can't use I, O, or Q, and so that's 26 possible alphas minus the 3. That's 23 times 26 for this one, times 23 for the same reasons as position 2. And then finally, the last three are each 10 numerical characters possible for each position. And then when we multiply all this out, we have 137,540,000 combinations that are possible. This would be terrible to enumerate by hand. And you can see that this number is ample enough to cover the 25 million drivers that we have in California at any one time. And it should last for quite a number of years. Okay? So the question that we have is, what if these different tasks didn't have special rules, and if they were all pulled from the same set of characters? For example, what if each position was picked from the same pool of 10 numeric characters? Would that simplify the counting methods? And the answer is yes. So there are 4 different methods of counting when the pool of characters are the same initially, and they depend only on 2 factors, which is whether or not the combination is ordered, whether or not the different objects you pull out from the pool are replaced with each position filled. Okay, so let's before we get to the 4 different methods of counting, let's make sure we get a certain mathematical concept down, which is the concept of factorial. So for factorials are as follows. For positive integer n factorial, this is the notation, n exclamation mark, and factorial is the product of all the positive integers less than or equal to n. And this is way easier to explain in numerical form, which is basically 7 factorial is equal to the multiplication between all of the numbers from 7 all the way to 1. Okay, so it's just basically a countdown, and then you multiply everything in that countdown. And the most important thing to get on the slide is the following, is that please notice that the tail end of any factorial is also another factorial, okay? So the largest number in this set is 4, and you can easily cancel out this portion right here, 4 times 3 times 2 is 1, from 7 factorial just by dividing 7 factorial by 4 factorial, okay? So that's how you cancel that out. Alright, and then there's just one more accounting thing. So 0 factorial is just 1, and that is just because we want it to be an identity, and whenever you do an identity for multiplication or division, it's always 1, okay? That's it. So let's jump into our counting methods. So the first method is when the combination is ordered and without replacement, okay? So here's a real life example. In 1969, during the draft lottery for the Vietnam War conscription, in this basin right here are 366 balls, 1 for each birthday, 366 because February 29th for leap years is included in this. And then from this basin of 366 balls, we're picking 195 balls to be sent to be deployed to war. Okay, and it's ordered because the order in which the balls are picked is the order in which these units will be deployed. Okay, and there's no replacement because it doesn't make sense to call the same birthday twice because they're already going to war. Okay, so let's figure out this numerically. So from the first position, you have 366 possible balls to pull from. You remove 1 birthday, and then now you only have 365 birthdays to pull from, and so on until you reach the 195th ball. And during the 195th ball, you only have this many combinations: 366 minus 195 minus 1. Okay, so 1 less than 195. And in factorial form, that's just going to be 366 factorial divided by 366 minus 195 factorial of that. Okay? And we can generalize this into the following, which is n times n minus 1 times n minus 2 all the way to n minus 1 less than k. And in factorial form, it's just n factorial divided by n minus k factorial. Alright, so that's the generic equation, expression for the number of combinations you can have if the combination is ordered and without replacement. Okay? So let's go on to the next example. What if we still kept the combination ordered, but there is replacement, which means that every time you pick the value for the position, you replace that object into the pool of possible options. So here's the example. It's a variation of the license plate example we had before. So instead of the base plate code, which is the one that you're automatically just given, what if you wanted a custom plate? Okay, and so in a custom plate, you can pick any of 36 possible characters, so alpha, all the alphas and all the numeric characters for any of the 7 positions you want. So there is, and it's ordered because you want to say something meaningful, like for example Gandalf. It matters that G is before A and A is before N, and etc. And there is replacement, as you can see here, because we see A, and then there's A again, which means it was put back into the pool of options. Okay? So let's write something down numerically expressing how this combination can be figured out. And what we have is this. So for each of these 7 positions, we have 36 options, and because we're replacing, we're not taking out, like say G from the pool every time we pick out a position. This number 36 doesn't change for each of the positions, so we end up having 36 to the 7th possible combinations. And if we generalize, it's just n to the kth position. Okay, very simple to calculate. This is probably the easiest thing to calculate for all the 4 different methods. So now it's going to get a bit more complicated because we're going to get into unordered combinations. So let's start with unordered without replacement. To illustrate this example, I'm using John Cena. For those of you who aren't WWE fans, John Cena is a pro, and that's pro in quotation marks, a pro wrestler. And here's a scenario. So John Cena is hungry. He has an open package of M&Ms with only 6 pieces left. He wants to eat 4 now and save 2 later as a post-match reward. Okay, so here's a schematic of what's going on. So he has, again, 6 M&Ms. And we're just going to say they're all different colors. And he only wants to eat 4 now. And they're going to go into his mouth. So they're unordered because he's going to pick 4. It doesn't matter what 4 they are. Because he's going to eat them all in one go. Shove them in his mouth. And there's no replacement because they're going to go in his mouth. Okay? Okay, so the strategy for this is to pretend that this combination is actually ordered. So ordered, pretend that it's actually ordered. And then calculate the number of combinations for that. And then just divide out the number of ways 4 numbers can be arranged because there's only 4 M&Ms, okay, that he's eating. All right, so let's do that. So again, we have, so there are initially 6 M&Ms. So the first M&M we can pick, there's 6 different ways to pick. After he picks the first one, there are only 5 left to pick from and so on until we have 4 M&Ms. But if you notice here, this is like the beginning of a 6 factorial, and we just need to divide out the remaining of the factorial, which is 2 factorial. So that's where this comes from. That's why we're dividing by 2 factorial, okay? All right, and then now we need to divide out the number of ways 4 M&Ms can be arranged, which is this right here. Basically just 4 factorial, okay? So let's generalize this. So this is basically n factorial divided by k factorial and divided by n minus k factorial. And this here can be abbreviated into what is called the binomial coefficient. And in this format, this is read as n choose k. All right? So binomial coefficients become important when in next week's lecture about distributions. So just remember to keep this in mind. Okay. So let's continue on to the next method. And this is the most difficult one to understand, in my opinion. So we're again going unordered, but this time there is replacement, okay? And the example I'm going to use here is 31 Baskin-Robbins flavors. So imagine you're going to an ice cream shop, namely 31 Baskin-Robbins. There are 31 flavors to choose from, and you want to get a 7-scoop cone, because you deserve it, okay? Now, of these 7 scoops, they can be any flavor you want. They could be all vanilla. They can just be chocolate, half vanilla. They can be anything. They can be anything you want from here, okay? So there is replacement. And it's unordered because it's all in one scoop. You don't care what order it is as long as it all goes in your mouth. All right? Okay. So the same strategy from before is not going to work. We can't just pretend that this is an ordered situation, calculate the number of combinations as if it were ordered, and then just divide out the number of ways it can be arranged. That won't work. What we need to do instead is to think about the problem as if it were a histogram. Okay? So let's turn this into a histogram right here. So imagine you have 7 scoops to distribute within this ice cream flavor histogram. So you say you put 1 here, so you put 2 here, you want 2 scoops of that flavor, 1 scoop of that flavor, 1 scoop of that, and maybe 2 of that. That's how that would work. Let's now turn this grid into an actual line histogram. Okay, so this is flavor number 1 here. We have flavor number 31 here. And then you can distribute your scoops anywhere within these different flavor bins. Okay, so these are flavor bins. Now, what's important here is that there's an order of, the order of scoop to divider is very important to keep a note here, okay? And you'll note that if we're going to keep track of whether a scoop is next to a divider, these ones don't matter because they're always going to be at the end, right? Which means we have the situation here where we got rid of the end dividers, and which means now we have 30 dividers, 31 minus 1. And now we have 7 scoops to keep track of, okay? And we want to know what the order of scoops are next to dividers. Okay, so this is what it looks like. What we have here is this. We have the number of combinations of 37 objects, that is 30 dividers, and 7 scoops possible, okay? And because the scoops can be distributed in any of these flavor bins, you want to cancel out the number of ways that 7 numbers can be arranged, because it doesn't matter how the scoops are arranged within themselves, and it does not matter how the dividers are ordered within themselves. And when we divide these two things out, all that is left is whether or not it matters a scoop is next to a divider, okay? And so with that, then we get this number right here, which is just 37 factorial divided by 7 factorial divided by 30 factorial. So again, take your time with this slide and try to figure out how it makes sense. Then we can address that in class if you're still confused, or you can email me. But remember this. Okay, so let's generalize. So the general form of this is just n plus k minus 1 divided by n plus k minus 1 factorial divided by k factorial and by n minus 1 factorial. And in the choose k format, it's going to be n plus k minus 1, choose k. All right, so that's the notation for that. And if we summarize here, the methods of counting are as follows. In this table, if we have ordered without replacement, and that's again the Vietnam War draft lottery example, we have n factorial divided by n minus k factorial, okay? And if we have ordered with replacement, then it's just a simple exponent expression. Remember that it gets a bit hairier when things aren't ordered. And so for the case of unordered without replacement, we just pretend that it's ordered and then just divide out the possible arrangement of the combination you have, which is just n choose k, which when you put in factorial form is n factorial divided by k factorial divided by n minus k factorial. And finally, the most difficult situation is when you have unordered and with replacement. That's the ice cream example. And it's just n plus k minus 1, choose k. And in factorial form, it's n plus k minus 1 factorial divided by k factorial divided by n minus 1 factorial. So it's not super critical that you remember how to do all these, just that you know to look these up when the situation arises, okay? All right, so now that we have this table, then you know that it exists, and you can always go back to this. Let's move on to the next set of concepts, which is set theory. Okay, so why are we talking about set theory? This is why. So we've so far been talking about real objects in real containers. For example, scoops in ice cream cones, lottery balls in a bowl, M&Ms in John Cena's hand. Okay, but now let's move away from these real objects in real containers to mathematical objects in mathematical containers. Okay, and so to analogize it, it would be like these bingo balls here would be these elements here, and this container where the bingo balls are going to be these brackets representing a set. So let's get some definitions down. So a set is an unordered collection, unordered, super important, unordered. Okay, it's basically a matter of composition. All right, collection of distinct elements. So a set is denoted by these curly brackets right here, and you can fill the set with its elements. So distinct elements, what does that mean? It means each element is different from each other, okay? And remember when I said unordered is important? This is what this means. You can put 1, 3, 2, Doesn't matter. It's the same set. Okay? A 3, 1, 2, 1, 3, 2, 2, 1, 3 does not matter. Okay? Alright. So we know what a set is. Now let's focus on the elements, or the things that are inside a set. So for a set of A equals 1, 2, and 3, we can say that 1 is an element of A, denoted by the symbol right here, epsilon. 1 is an element of A. It's epsilon because it looks like an E. E looks like an element, like beginning of element. So that's how you remember that. Okay, so you can say it's an element of the set, it's a member of the set, it's contained in the set, it's included in the set, it's all the same. Okay, so let's so this is one way to specify a set. It's just by denoting its element in this way, individually. Or you can specify a set by using a rule. For example, A equals 1, 2, and 3, and you can just say, instead of saying 1, 2, and 3, you can just say X. And you can say, so A equals the set of X, given that X equals 1, or that X equals 2, or X equals 3. And so this right here, this symbol right here, the pipe, just means given that. And for those of you who might recognize this notation, it's used also in conditional probabilities. Okay, so this will be important. Please keep this notation in mind. Okay. So you can have this as a rule, or you can have an equation that is more encompassing. For example, here. So say your set is 3, 6, 9, 12, and you can see there's a pattern, right? Basically multiples of 3, and it goes on to infinity. You can have this rule instead. You can have X, given that X is a natural number that is a multiple of 3. So this is more of a general rule than what we saw before. And then from this, I want you to please note that sets can be infinite. Okay, they don't have to be enumerated distinctly. They can be infinite, on and on and on. Okay, so here's another property of a set. A set is uniquely identified by its members. So, for example, these sets are all equal. X is an even prime, which is 2. X, given that X is a positive square root of 4, which is also 2. And then X, given that X is the number of feet Kathleen has, which is 2, these are all equal to 2. Okay, so these are no different from each other. These are all equal. These are not considered different in terms of set theory. Okay, so let's talk about when a set is equal to each other. So sets, so this is an informal way of saying how sets are equal, but let's be more specific. So sets A and B are equal if and only if every element of A is an element of B. So remember this notation right here, epsilon, A is an element of B, and every element of B is an element of A. So there's some reciprocality right here, okay? Alright. Let's talk about the number of elements of the set. So the notation for figuring out what the element of a set is this right here. It's like the absolute value bars right here. So for example, the number of elements in this set is 3. Number of this is infinity because there are these ellipses here. And this one is a bit more complicated. So you have this set here, X and Y. It can at most be 2, and it can at least be 1. Why is that? Why is there a range? And it's this. It's for the case in which X equals Y, then really it's the same thing, right? It's just 1. You only actually have one number. Because remember, a set can only have distinct elements, right? So if these two are the same, then it's 1. We don't know that, but if they are, then that's what it is. So this is the range of how many elements can be in a set. Just keep that in mind. Okay, so let's talk about subsets. So a subset is, so it's denoted by this sort of like long C. It's basically a sideways U, is what that is. So it's denoted by A is a subset of B. That's what this symbol means right here, okay? Just remember that. And I sort of remember this because there are 2 points here and there's only 1 point of contact here, so I just think that B is bigger, and so A is encased in B. I don't know, whatever you need to do to remember that that's what that means. So A is a subset of B. Okay. So what does subset mean? It means that if A is a subset, sorry, if X is an element of A, then it has to also be an element of B because A is encased in B. Okay? And then we can use, now that we have this subset notation, we can further define the equality of A of two sets. So sets A and B are only equal if and only if A is a subset of B and B is a subset of A. So this is, again, this reciprocality here. Okay? All right. So let's just cover up what basically an interesting case, which is the empty set. So a set with no members is an empty set. It's considered a set. It's indicated by this here, which is going to call the null. So null, the null set. So null is a subset of every set. Okay, just note this, and it's going to be a bit complicated. It doesn't usually count into the number of sets, but sometimes it does. I'll let you know when that is. But normally, for most things except for the power set, you don't want to count this in when you want to count the number of elements in a set. You just kind of ignore that. Okay. All right. Let's move on. All right. So there are three basic set operations you can do on sets. And it's this. You have union, represented by this giant U symbol right here. Then you have intersection, which is just the opposite of union, which is why it's like an upside down U symbol here. And then finally you have complementation. Sometimes it's called difference, and represented by the backward slash. Okay? All right. Union. What is union? Union of sets A and B is a set that contains all the members of A and all the members of B and nothing else. And essentially what it means is this symbol, union, effectively means or. Okay? So it's anything that is in A or in B. So it's X given X is an element of A or X is an element of B. Okay? And so an example is this. We have sets 1, 2, 3. We have a set that has elements 2, 3, 4, and then union is anything that's not, basically you want to smush these things together and then remove any redundancies, right? So it's just, you have 1, 2, 3, 1, 2, 3, and the only thing that's different here is 4, so you want to add 4. Okay? All right, let's go on to intersection. Okay, the intersection of sets A and B is a set that contains everything else, everything that is a member of both A and B and nothing else. And what this turns out to mean is that this symbol, intersection, again the upside down U thing, effectively means and. There's a restriction that it must fulfill two restrictions basically, okay? So it's the set of X given that X is an element of A and it also has to be an element of B, okay? So in the previous example, using the same example, we have a set that has 1, 2, 3, and a set that has 2, 3, and 4. The intersection of these two is anything that is the same between these two sets, okay? So it's the intersection, it's where they overlap. So it's not 1, because we don't have 1 here. It's 2, and it's 3, and then it's not 4. So it's basically just 2, 3, okay? It's what they both have in common. And we have another definition here, and it's just that sets A and B are disjoint if the intersection of A and B is the null set, meaning there's absolutely no overlap whatsoever. Okay? All right. And finally, we have complementation. So there are two types of complements. The first one is a relative complement of sets. So the relative complement of sets A and B is the set of elements of A that are not in B. Okay? So it's the opposite. So it's the slash in the direction opposite what you normally use for division, okay? So it's this slash. And it's the set of all things that are element of A but not an element of B. So in this example here, it's we have 2, and we want to see if it's not in B, and it's not, so that works out. We have 3, we want to see if it's not B, it is in B, so that doesn't count. And we have 4, it's also not, it is not in B, so that counts too. So what we have finally is this. Okay, and the important thing to know is that this is directional. Okay, you look at this with reference to that. All right, so it's very directional. Okay, and then finally we're going to talk about absolute complement, which is the more common type of complement we're going to be talking about when we go to probability proper. Okay, and so imagine universe U, and this is the only time I'm going to mention U. Okay, so there's a universe, and it has all the elements that we want to consider. Then in that case, the absolute complement denoted by this C right here, little c, is everything that is in the universe that is not A. Okay, so this just means not A, because we're accounting for the whole universe now. All right, so remember this. This is going to be super important later on in probability. All right. Okay, so let's move on. So there are some properties of union and intersection to take note of. So some of them will make, most of these will make pretty intuitive sense once you draw them out. But basically, I'm just going to go rush through them. Take your time later on if you want to understand them more, but I'm just going to rush through them. And it's just basically the union of two sets. It doesn't matter what's before the union sign. It's the same thing. Union of A and B is equal to union of B and A. Same thing for intersection. Associativity means you can find out what this is first, and then do the union of both. Same thing for intersection. Distribution laws means if you have to find the union of A of the union of B and C, you can just sort of find A union of B and A. Sorry. Delete that. Basically, you can just find the distribution. So you have the A intersection of B of, so the A, sorry, let me start over. You have the A intersection of the union of B and C. You can just pull out B and C individually. So you can find the intersection of A and B, intersection of A and C, and then unionize those two things. Okay, so you can do that. And then finally, the most complicated thing is De Morgan's law right here, which is that the complement of a union is the intersection of the complement of the different sets. Okay, so I'll just do one example real quick. So you have A, then you have B, and you've got the universe right here. This is your intersection. Okay, so this is what this is right here. So the complement is everything that is out here, right? So, okay. And if you do the union, so that's this here, okay? So let's find out what, let's find out what this is then, okay? So we have, again, the universe. We have two circles, A, we have B. Everything that is not A is here. And then everything that is not B is here. And then, yeah, this is really messy, I know. But hopefully what you could see is that this bit right here is left blank, okay? So that's what that is. So if you're ever confused, just draw these things out. It'll make sense to come back to it after you finish the 2 lectures, but just trust me that these work, and work these out for yourselves later, all right? Okay. Let's move on. Okay, so what we have now is, let me just get back. Okay. All right. Okay, so let's talk about collection of sets. So far we've been talking about sets with discrete elements in them, like say 1, 2, discrete numerical elements in them. But an element can itself be a set. So you can have a set of sets. You can have a set of sets. It's sets all the way down. Okay? Whenever you have a collection of sets, we usually tend to, at least in the math world, we tend to label it with a font called Fractor. And Fractor is a terrible font because it makes letters look unlike themselves. For example, this is supposed to be the letter A. This is collection set A. It looks like a U. I know, it's terrible. I'm sorry. But that's how it is. So this is a collection. It's in Fractor script. And it's a set of sets, right? There are 3 elements in this set, and they're each sets, okay? So 3 pairs of brackets inside the bigger bracket. All right. And so the union of all the sets in this collection is just the union of all the elements in each of the sets, okay? So it's X, given that X is in sum, A, that is an element of, so that is a subset, so it's a set in this bigger collection of set A, okay? A collection of sets is pairwise disjoint if any 2 sets from the collections are disjoint. So if you pick any 2 sets from this collection, they will have no overlap. That's what that means. Okay, that's just a particular kind of collection. It doesn't have to be that way. All right, so let's talk about a special kind of collection of sets, which is called a power set. It's not fract. So this is usually denoted by like a row, but it looks like a P. So I've used this character here that sometimes people use. So the power set, not the probability. Okay, it's a P, but it's the special character here. The power set of 1, 2, and 3 is all the possible sets you can get using these 3 elements, right? So it's sort of, this is like a form of counting, right? So you can have the null set. Again, this is one of the situations where you count the null as a set in the number of sets, okay? So you're now in the power set, only in the power set really, do you care about the null set when you're counting the number of possible sets you can have. So you could have just a set of each of 1 element each, you can have a set of 2 elements each, and you can set up 3 elements, okay? And so if you want to count how many possible sets are in a power set, it's just this. It's 2 to the n. Okay, so however many elements you have, which here is 3, then you have potentially 8 different kinds of subsets. Okay. So going from the power set, which is a special form of a collection. Now we have a special form of the power set, which is called the sigma algebra. It's a funny phrase. It doesn't matter. We just call it S in Fractor, okay? I know, this looks like a G. It's actually an S. I know, this is actually an S. It's an S in Fractor script. I'm sorry. So the sigma algebra S is a power set of the set S that satisfy the following 3 properties, okay? So the first is that the null set has to be an element of the sigma algebra, which is a power set, by the way, again. And if A is in an element of this power set, then the complement is also in this sigma algebra as well, okay? Which means that this sigma algebra is closed under complementation. And then finally, the third property is if A1, A2, all the way to whatever is an element of the sigma algebra, the union of all those is also an element of the sigma algebra. It means that sigma algebra is closed under countable unions, okay? And when you put that all together, this forms the basis for probability theory, okay? It's the collection of all events that can be assigned probabilities. We have not arrived at probability yet, but we've set up the foundation for which to apply probability and probability values. Okay, so in this lecture we've covered counting and we've covered the definition of set theory, which will hopefully give you a foundation for understanding probability theory. And in the next lecture we're going to cover this main thing here, intuitions. Alright, and so here are some sources. Hopefully the YouTube video page will have these clickable links for you. And yeah, good luck. See you next lecture.